So I'm very happy and proud to introduce a friend and colleague, Stefan Weber. We invited Professor Moshe Shoam and myself to the ISRACAS conference already 15 years ago with the idea of having an emphasis on medical image processing and medical robotics. So we're very happy that Professor Weber came here and agreed to give this talk. Just a brief some details about Professor Weber. He's now a professor of image-guided therapy at the University of Bern at the Faculty of Medicine. So he's an engineer at the Faculty of Medicine, which is a great achievement. He did his PhD in robotics with a Fulbright scholarship at the Charité Hospital in Berlin, and he did a postdoc in Munich, and since 2008 he's at the University of Bern, where he has done spectacular work, which he will talk about.
Thank you, Leo Joskovic, for the invitation. It's a great pleasure and honor for me. I say Boker Tov and Toda Rabba, as I wrote this down yesterday on my way from the airport with the taxi driver, giving some introductory lessons. Yes, I'm working at the University of Bern. This is a picture in Bern, basically from the top of our institute. We look to the 4,000-meter Swiss Alps. Bern is very old and has a strong and long-lasting tradition of biomedical engineering. It started more than 100 years ago with Theodor Kocher, who was a thyroid surgeon, and he was one of the very few surgeons who ever received the Nobel Prize and in medicine. And since then we have a long tradition in putting machines and instruments together in Bern. In the 80s, the invention of the artificial hip joint took place in Bern. Professor Maurice Müller, he was an orthopedic surgeon in Bern, and we could continue. And as of today, we have around 200 people at the University of Bern associated in different domains, working in different fields, all the way from image-guided therapy to image processing, cardiovascular engineering, and many other things. What I would like to talk about today is a little bit first on the role of robotics, and then we'll look into the story of image-guided cochlear implantation. And before I go into this here, I don't know if Björn is still around, whatever. I think the role of robotics in medicine is not so much the role of replacing surgeons by robots, as much as the surgeons like the idea to say they can sip a coffee while the robot is doing the work. The story actually goes completely different. What we say is that the robots can and should do tasks that the surgeons cannot do on their own, and therefore, come forward with new treatment systems, new treatment modalities that enable the surgeons for less invasive, more precise, more radical treatments, let's say for oncologic surgery. This will be beneficial for patients, and effectively in the future we will not see less surgeons, but we will see more and better treatments with the help of technology. That's our hope. And today I will talk about a little bit on the story of hearing implants and how technology can actually help to make happen that implants can be placed and implanted much better. And we say, it's an ideal setup to say, why can we have robots in this domain? Because robots are acting on a similar scale. The precision is much higher than human can do. Repeatability aspects and consistency aspects are playing in favor for the connection of hearing aid implantation and robotic surgery. Why are we doing this? The story is that as of today in the world we see around 35,000 cochlear implantations per year, and the cost of the treatment is around $40,000 to $50,000, euros, Swiss francs, whatever you take. And the quest is to reduce the costs of both the implants and the implantation procedure itself, which would make it more attractive, of course, for the healthcare systems in the first and the second world, but eventually it would also kind of dilute into the third world, where most of the patients who are in a strong need for treatments cannot be treated because it's simply too expensive. The rate of cochlear implantations in China, for example, is at a very small fraction of what could be done in the normal ways according to the standards of the first world, but it's simply a matter of cost. So we claim and we believe that we can simplify procedures, we can reduce invasiveness, which is favorable for the patient to have a small scar and less blood loss compared to a big scar, and a lot of trauma in the bone and in the soft tissues. And effectively also what we see what we do discuss with the implant manufacturers is the idea to actually make the implant, the future generations of cochlear implants, much simpler, because the way we put them in is much more organized and much more simple. So we have framed the term minimally invasive and atraumatic implantation. That means for an implant electrode, I'll show you a picture of a millimeter. You don't make a big access into the natural skull base on the side of or behind the ear, but rather you just drill a small hole and go in. And to be able to do this, we apply image guides on a microsurgical level, and we look into tool-tissue interaction just as conventional CNC machines would do that, very advanced sensing and control systems. Okay, and now I talk about this cochlear implantation story, and before I do this, I show you a picture from a neurosurgery OR. Do I have a laser pointer? I know I have one. I don't know how many people of you are familiar with image-guided surgery. What happens there is there a camera here tracks the position and the orientation of instruments relative to the patient. This is a neurosurgery, so we have the patient head here. The open skull is possibly covered with some drape here, and prior to the surgery, the patient has received an MRI or CT scan, and then in the surgery, the tracking allows the tracking of the instruments, and the surgeon effectively can see on the screen where he is with his instruments relative to the so-called medical image data. So, and this allows him to view, for example, here on the picture of his microscope, he can see inside, he can see on top of the brain in a magnified glass, but he can also see what the image guidance system tells him where the medical image data is. So he can see here, of course, he can see the fiber tracks of the nerves inside the brain, and of course, once he's bringing in his instruments, he can actually see where the instruments are. The question is, how accurate is this? I don't know if you're familiar with accuracy, but if I would ask you, do you think what he sees is accurate to 1 millimeter? Maybe some people raise their hands. The question is it somewhere between 1 to 3 millimeters, or is it even above? We look at this in the OR, with all the circumstances that decrease the accuracy, and we see the accuracy in the OR effectively somewhere between 3 and 5 millimeters. So that means if the surgeon thinks the tumor is here, it might be well off by a couple of millimeters. And of course, the surgeon cannot see this. It's like doing surgery to yogurt within cottage cheese. Okay, you don't see the tumor blinking in red, telling the surgeon, this is the tumor, take me out. So it's really same structure, same color, and so on. And the question is, with this accuracy, you can only do that much. But if you go to cochlear implantation, we have to drastically increase the accuracy. I will talk about this in a second. So cochlear implantation, you see here the inside of the ear. This is the middle ear with the ossicles. Here's the cochlea. This is a snail-like structure that transmits the sound waves from the middle ear and converts them from a mechanical actuation into impression of the hair cells of the cochlea, which is then further progressed towards the brain. If patients have a problem, significant or complete hearing loss, the treatment is to put an electrode inside the cochlea, and inside the electrodes we have little metal plates, metal connectors, and the implant itself sends the signals through the electrode and excites the cochlea hair cells inside. And the question is, how do you put that implant in, and under which level of invasiveness, and of course how long has the patient to stay in the hospital. We look here a little bit bigger into the picture. What we see here, the first part is between the middle ear and the outer side of the patient is the bone. It's called the mastoid temporal bone. It's the hard bone behind your ear. You can feel it with your fingers. One has to go through this by drilling a hole effectively, putting the electrode through here. Then the next part is the cochlea, and the surgeon has to effectively open the cochlea, drilling a hole into the cochlear wall to access the inside of the cochlea, and then effectively he or she can put in the electrode. It's a microsurgical procedure. It's very difficult. What we see here is what happens on the outside of the patient. There's a big incision. You see here the skin flap that's created a couple of centimeters behind the ear that the surgeon opens, and the surgeon mills away, starting with the size of a 2 pound, 2 francs, whatever, like a coin like this size in diameter on the outside of the skull, and the surgeon progresses with this milling forward into the ear, trying to avoid most prominently the facial nerve. This is a structure that controls the muscles and the senses in the face. You do not want to screw with the facial nerve. What you see here in the picture is the size of, it's called mastoidectomy, the removal of the bone behind the ear that you have to do in order to place a submillimetric electrode. So this is very, very excessive. In Switzerland we say it's about, instead of drilling the Gotthard tunnel through the Alps, we just bomb away the whole mountain. This is the problem here. Okay, and I tell you why on this picture why they actually do this, because the facial nerve is at risk. If you look from the outside to the anatomy, 20 millimeters below the bone surface, you have the facial nerve, which is responsible for the whole face, and next to it is we call it corticotupum. It's the tongue nerve. It's responsible for the taste and also for the glands inside the mouth. And between here, you have an area of around 2 to 3 millimeters only, through which the surgeon has to drill a hole in order to access the middle ear and ultimately the cochlea. And as you see already here, 2 to 3 millimeters, you cannot do this with the normal conventional systems that I showed you before in neurosurgery. It's impossible. And this is why today surgeons just go and open up the skull in a big manner. And we propose, as engineers, we say, if you have an electrode which is 0.8 millimeters, you can effectively drill a hole which is a little bit bigger, and you put the electrode through all the way into a cochlea. And we started, roughly 4 years ago, we started a big research project and to cover with this. The problem here is, again, you saw the 2.5 to 3 millimeter, this is the corridor at which you can go in. Your electrode is 0.8 to 1.2 millimeters. You effectively have to create a 1.5 millimeter drill hole, and that means on each side, between the drill hole and the nerves, you have around a 0.5 millimeter space. Now imagine, take your fingers and look at the 0.5 millimeter. It's very, very thin. It's very, very delicate. Okay, and that means we have to be very, very accurate in our robot accuracy. And if you think of it, it's not only the precision of the robot itself, being able to reach a certain precision, it's about the whole error chain of image data, registration, calibration of tools, and so on. And we have to look into this. Before we do this, I give you a little bit of an idea of what people have done in the domain of minimally invasive cochlear implantation. Of course, people say, if the surgeon is aware of it, he or she can try to be less invasive. It's impossible to drill just a small hole because you'll never be able to drill from the outside of the skull blindly into the space between the two nerves. Then we have the domain of image guidance, then robotics assisted, that's one here, and then also stereotactic frames. So some brave surgeons actually have tried to use conventional navigation systems, segment the structures of the inner ear, place a target, and then align a surgical drill with, as you see here, the group of Robert Machstein and Thomas Lennart in Hanover in Germany. But the studies just found it's, you can do it, but it's not really helpful because in the end it's too inaccurate to really be relied upon. So people moved on, and several groups have tried to use robotic systems. As you see here, the big industrial systems, they are tracked. You see the little dots here to track the position in space. However, all of these attempts went nowhere because the accuracy was not reached, not by the fact that the robot is not accurate, but the whole error chain was not kept in place. So we say accuracy is around a millimeter, but it's not sufficiently safe, and therefore they cannot take it forward, let alone the fact that the industrial robot is difficult to put into the OR. So a group of engineers and doctors at the Vanderbilt University in Nashville in the States came forward with the idea of using bone-anchored screws, 3 millimeters in diameter, that you put through the skull, and then you put a parallel kinematic structure on top, which can itself orient and position, and then through a hole in the top, you can put your drill bit and drill the hole very precisely into the head. It's very interesting. They call it a mini stereotactic frame. It's somewhere between a stereotactic frame and a robot system, because in the end, the robot during the procedure will not move. It will just align once to the correct orientation relative to the skull, and then you put your drill bit in and drill the hole. Okay, so here's a similar attempt, same team. This is a passive stereotactic frame, and here you see how they do it in the OR. They open up a part of the skull that plays the 3 screws, and then they do a CT image in the OR, take the CT image to a computer, make a planning, and then in real time, more or less, they have a CNC machine next to the OR and drill a template, you see here, from plastic, that after 15 minutes of sterilization, we mount onto the patient, and then in the middle of the template, you have a hole that exactly guides the drill bit into the head. So this was for the first time an accurate level of image guidance, I would say, on a brute force engineering attempt, but it reached the accuracy. So here we see the accuracy levels. As I said to you earlier, we have the problem of accuracy. The robotic approaches were above the 0.5 millimeter accuracy, and then Rob Labadie and his team, they reached actually the 0.3 millimeter threshold with their template. So that gave a boost basically to all the teams in the world who tried to come forward here with this procedures. We started 4 years ago in Bern to develop an accurate robotic system for cochlear implantation that you see here on the picture. It's a small 5 degree of freedom serial arm. It weighs 5 kilograms. You can mount it to the OR table. The nurse can actually mount it to the OR table, which was an important requirement. There's no additional chair that you have to wheel in with the robot on top. So you mount the robot. We have we call it a non-invasive head holder. It's like a motorcycle helmet with a vacuum cushion inside. You put the patient inside, you pump up the vacuum, and then the patient is kept in place. And then we have a very, very precise optical tracking camera that works to guide the robot. You see here the drill bit. This is a conventional drill system that will, in the end, drill the hole. The aspects of our research were imaging and planning, precision guidance, and I will talk about this later, also security aspects. So the first part is that we try to come forward with an ultra-precise way to co-register the image data with the patient. We have an image data set of the patient. We need to align it during the surgery with the patient. How do we do this? We place very small screws into the patient, the skin, before the surgery and before the imaging. You see the screws are very small, this is my pen here, and if you see this in the OR, the screws are going directly through the soft tissue, through the skin. We have a little bit of cover around to make sure that the small screws are not just getting covered up again by the soft tissue, so they kind of stay open in a little convex hole, and then the robot can go in later. You also see here the hole, but we'll talk about this later. And we were able to achieve an alignment accuracy of around 1.5 tenths of a millimeter. So that means we are already very precise. Then another project was to come forward with a small little, now we call it app, a little planning app that would allow a surgeon to plan a trajectory. What you see here is the gray is the bone. In yellow we see again the facial nerve. In orange the chorda tympani. We look a little bit from the side here, and the surgeon with the software can effectively plan very nicely a trajectory from the outside of the skull towards the cochlea inside the ear. And the computer model, or the computer can tell or tells the surgeon, whenever he or she plans it, how far are the distances, as you see here, the red lines, tells the distances to, let's say, the facial nerve. So in this picture here, the distance between our drill hole and the facial nerve is 0.5, roughly 0.5 millimeter. So with this tool, the software, the surgeon can actually sit down and make the plan, and the planning aspect actually becomes a very important aspect for the surgeon. Instead of just going to the OR and starting to drill a hole and look what's happening, he has to sit down prior to the surgery and say, what's the problem, where's the facial nerve, are there any anatomical variations that he or she has to respect. And in the end, he has a pretty clear understanding of what to do. Also in Switzerland, we used to say, it's the planning aspect that makes you safe. If you go hiking in the Swiss Alps, you have to have a map. And the night before, you look at the map and you say, I'm going to hike here, and if this bad weather, I go down here, and so on. You just don't go hiking the next morning, right? So this is a little bit the understanding here. So then the software sends the data over to the robot machine, and then the next day, or a little bit later the day, you do the surgery. We see here we call it the registration tool. It's a very thin tool that goes into the screw here. We see this here. The robot has a force torque sensor. So while the robot goes into the screw, the robot can actually read the lateral and the perpendicular forces and can minimize the lateral forces. And by that, the robot can digitize the position of the screw space with a very, very high repeatability. We tested this under laboratory conditions to be in the order of 3 to 5 micrometer, depending on the temperature and the daylight, whatever. But it's very nice that the robot comes always back to the very same position, and it makes us to have a registration accuracy of less than tenths of a millimeter. Then tracking was important. As you can imagine, we have an optical tracking, so a stereo camera system looks to the patient and also to the robot. And I'm not going to go into the details here, but the tracking accuracy at the moment is 15 micron, which is it's very impressive, but it's actually possible, and it plays towards our goal of accuracy. And at the same time, we also have a calibration issue here. We have to be able to calibrate the tools relative to the robot very accurately and also very reproducibly. We can do this now with tenths of a micron. It's not to be going into detail today. So we carry out extensive drilling tests on cadaver heads. That's our model before we go to the patients. And what we see here is one of the results from a cadaver head. Again, you see here in the background, you see the cone, the CT image of that cadaver head's ear. We see again the segmentation of the facial nerve. We see in blue, or you might see it not too well, but in blue here was the originally planned trajectory, and in pink is where the trajectory happened to be afterwards. So it's almost perfectly aligned, and the accuracy that we have achieved over, we said 8 human cadaveric heads was 0.15 millimeters, with a variation, standard deviation of 18 microns. So again, take your fingers and think this is very, very small on a very, very small scale on a human head. So if you look at our accuracy plot again, this is where we are now after extreme optimization of the accuracy. It was not like extreme optimization of the robot, it was looking at the whole workflow, at the whole thing from imaging to planning to registration to calibration, and really squeeze every micron in the whole work chain here. So we had the accuracy that was about a good year ago. We said, okay, great, very nice accuracy, and we said let's move forward now to patients, and really prove that we really want to prove the story that such a machine can drastically reduce the invasiveness of the procedure itself. So here's some pictures that I would like to share with you. This is what we do at the moment in OR. We prepare for a clinical trial which we will effectively start next year. So already now we go to the OR, we have the whole OR team set up. It's like a real world benchmark. The doctors operate, they put sterile gloves on and so on. We have the cadaver head here, it's draped, the robot is here, it's also draped. You know, the surgeon does everything he or she will do in a normal procedure. Then we bring in the robot drills a hole. You already see how we have only the 4 screws here, a small incision with a drill, through which the drill can go and drill the hole. Then the robot drills the hole. You see here the robot. We irrigate, of course, it's a very hard bone, this is why it's called the mustard. It's a very hard bone, so we have to cool it and remove the debris. And then in the end, after the implantation, you actually see we have the screws here. The screws will go out at some point as a part of the surgery, but you see the small incision, and here comes out the implant electrode. And this is the ear cuts of the ear. And now if you compare this to the picture that I showed you before, on the level of invasiveness, where you see here you have a huge opening on the side of the skull. In order to be able to drill a small hole into the bone, we see here the size of the level of invasiveness with what the robot can do. And effectively, this is also what a surgeon would do without a template. It's a really massive opening, and with the robot, you can just drill a hole very neatly where you want to have it. So, in the third part of my talk today, I talk about safety. As you can imagine, we are all aware in Bern of the fact that if the robot would drill in our first or second or third or 10th patients into the facial nerve, not only the project is over, but the career is over of our ENT surgeon, and also possibly mine. I will never come back to Israel, not at least for a presentation. So safety is really, really important. So there are military people here, and I know in military redundancy plays a big role. To be able to cope with an error of one system, you bring in another system. This is what we do with a system called force-based dose estimation. When we drill a hole into the bone, you see here in the schematic, you see the bone, you see the drill bits going through the bone, and what we also see here is the force that the robot can read while the robot drills into the head. So we see this force over the path. And of course, if you look at the CT image, what you see in the CT image is a representation of density. That's what X-ray does. So we say if the color here is bright and white, then there's a high density. That means also you have to have a high force to go through, roughly. And if you look at the planned trajectory into the head, that you see this in green here. And if you drill with the bone, and when you drill with the robot through the bone, you can actually look at the force, and you can compare the force to many possible trajectories that are in a little space around the planned trajectory. So this is the graph here. In the middle, you see the planned, in orange, the planned hole into the sleeve, and here around you see colored dots around 600 of possible trajectories. And what we do here, we compute a correlation between the force vector and the density vectors, and we do this in real time for those 600 trajectories. And what you see here, if I go back here, I can play the video again. When it goes in, when it drills in, you see how the computer computes the possible position independent of tracking and robotic accuracy. It just looks at the force and it tells us where it thinks it should be. And we can really nicely use this topic to say if the tracking and this information deviate from each other too much, then we say something is wrong. And either the tracking or this system is wrong. So we know by the differential analysis that things should be good or should be not so good. So technically we can turn off the robot tracking at some point into the head, and we still reach an accuracy of 3/10 of a millimeter by just looking at the force density correlation. We plan really to put this in place with the first patients to make sure we really nicely avoid the facial nerve. Another attempt that we are trying to understand, we call this functional image guidance. Here's the idea to use a neurostimulation system. So what it does is we evoke potentials in the facial nerve by putting little electrical signals into the mastoid, and outside on the patient we put electrodes onto the facial muscles, and we can actually read what propagates through the nerve, through the muscle, into the system. And I see the curve here, but there should be a little sinus put on here. So you have a monitor, it's a neuro monitor that can actually tell you how far, how close you get to the facial nerve. So we carried out a study together with the veterinarian surgeons in Bern, and the idea was to say, if the drill, you see here the schematic of the drill, if the drill goes tangential to the facial nerve, which you see here, then we would like to measure the effective distance, the shortest distance, closest distance, CB here, to the facial nerve with respect to the moving drill. And we would like to see what happens in the neural monitoring signal as the signal rise very close to the distance to the facial nerve. This is set up here. We did a couple of sheeps. We drilled into the sheep's head several times at different distances to the facial nerve. That was a very extensive study, lots of effort, as you can imagine. You have to have sheeps, you have to have a CT and an OR, you have to make sure you keep on with the regulations and so on. And here are two pictures. These are actually good pictures. We have, overall the results were not so promising, but we think we can improve it. What you see here again is the facial nerve from the side. You see here the path of the drill as it went through, and you also see here depicted over the distance. You see here the response in green of what happens when you get close to the facial nerve. So we see there's something ongoing. Same here, we get close to the facial nerve. This was an attempt to actually drill into the facial nerve, and it would also tell us here, okay, there is a response when you hit the facial nerve. We see that there's a good sensitivity, but actually there's a low specificity, so we cannot detect the false positives at the moment too well. So we have great efforts ongoing here to make sure we have another safety system in place to make sure we do not at any costs ever struggle with the facial nerve. Okay, and then insertion, that's the last part of the story. As you can imagine, when you drill a hole, that's only making sure you get there, but in the end you actually want to place an electrode. And this is a picture of the electrode. You see here the outside of the skull. You see our little drill hole here, and in between you see in white the electrode. And we show that the surgeon is actually capable of putting and placing the electrode through this tunnel into the cochlea. And you see here in green, this is the segmentation that we did on the computer to highlight the position of the electrodes inside the cochlea. There's a whole science associated with how we measure effectiveness of the insertion process and so on. We showed that it's possible to advance the electrode through the small hole, and that overall implantation time is in the end 35 minutes. So that really means you have the patient in, you cut a small hole, you put you drill a hole, you put the electrode in, you make sure it's working correctly, you put the actual implant behind the ear into under the skin, and then you close everything up. And the idea is that in the end, the patient can be treated in a very light way. You don't have to have a strong pain medication because you don't drill a lot of bone behind the ear. The incisions are very small and the surgery time is very short. And we hope that in the future we can do this with young patients. So what we see here, and this comes back again to the story of Björn Goretzky in the beginning, to us it's about, we do something with a machine that we cannot do by freehand. It's simply not possible. Okay? We see also, it seems to be less invasive and faster. We'll confirm this hopefully next year with the clinical trials. And of course it's very desirable for patients. I guess you can imagine if you would need to have a cochlear implant, you would go to a place, if it's established, where you say this would drill a small hole instead of making a big incision. And also if you compare it to robotic to templates, it's about accuracy, and it's also about being able to control the process. measuring all the variables in the process and effectively having this to increase the safety. What we also hear, because we talk to many doctors already on a European scale, is that they say they have to overcome the fear to do instrument flight. So you can imagine, the first pilots who actually turned on the autopilot and went through a cloud. They were brave men, right? Because they didn't know what happens, right? If the plane will ditch. And it's the same thing. What you do is, you have to rely on the system. You cannot control things anymore, right? You have to say, right, a line, and then the machine drills the hole, and that's a different story. It's independent of robotics. It's about psychology, I suppose. Huh? And then the quote that our ENT surgeons humans can make errors. So if you, as a human doctor, drill or make a bad implantation, you can say it was a difficult case or whatever, right? But if the robot makes a bad case, it's the end of the story. Leo Jošković knows what I'm talking about relative to the Robodog disaster many years ago. And with this, I would like to end. This is our team here in the OR. We are preparing for the clinical trials. I would like to thank everyone.
Thank you, Stefan, for a very impressive talk. I think you have shown that we are thinking, a lot of thinking, and really thinking into account all the aspects is really what makes what I think is an amazing tour de force. The numbers you showed are just unbelievable. So thank you. I'd like to invite a couple of questions from the audience.
Thank you for your enlightening presentation. Very impressive. I didn't understand how far you are from a real clinical trial you're about to start. And what's holding you? Why didn't you start yesterday with actual everyday surgery?
Good question. We have the approval of the local ethics board in Bern that we are allowed to do this procedure on a patient. At the moment, we fight with the Swiss FDA. Okay, these are bureaucrats that have to make sure that patient safety comes first. I agree with this. It's just a lot of paperwork. So I would say at the moment we have about this much paper that we have to create, and to show that it's safe. And we will go next year. It's just a matter of getting the signatures right, and then we'll just go as soon as we can.
Regarding the fluency, which whole fluency chain was the hardest part of the chain?
Let me think. I would say in the accuracy chain, you have a few screws you can turn, and you have many screws you can actually not turn. Okay, so you have a systematic problem with imaging, because in imaging, it's technically another system that is there. It gives you a certain resolution, but it also gives you a certain distortion in image data, and you have to live with it, and you have to go with it. Everything that relates to the robot, accuracy of the digitization and its tool calibration, you can actually look around and you look into industry. How does very precise CNC machines, for example, do alignment and calibration issues with tools, and how is that set up? That was not the hard part. The problem really for us is where our system links to other systems, and most prominently it's the imaging, where we really have to make sure the imaging is right. Yes, the imaging is 3D. We call it the resolution. The resolution of the imaging we use is 0.15 millimeters in all directions of a voxel. Right. Also in the C direction. I used the term computer tomography, but effectively it was full-beam tomography. So we have isotropic voxels with, in this case, 0.15 millimeters voxel size.
And this was really great talk. Two questions. First, what the problem is ahead, because it is not fixed rigidly in some ways. This is one question. The other one, 10,000 of cases. And the question whether we can go minimally invasive, this really nice way to do that, it's going to be expanded to millions because there are many millions of people over there that are really suffering health problem.
Thank you. So the first question relates to how rigidly can you fix a human head to the procedure, right? If you go to the shop floor, you have the device that you put something in with a human head, it will break. So in neurosurgery, people use Mayfield clamps, three pins that go through the skin into the bone. And we've actually seen in our experiments that there's still backlash in the Mayfield clamp system in the end. So with our setup here, you see it here, our motorcycle helmet, and this is actually not the patient position that's not correctly in this picture. It would go further in, and then the vacuum clamps will actually show that the movement is less compared to a Mayfield clamp. Okay, and at the same time, with the system, we track also the patient, and as soon as the robot drilling is inside the head, actually the kinematic chain is closed, and even if the patient will have very slight movements, not due to intentional movements of the patient, but more to bending and things, then the robot would compensate this through visual surgery. That was the first part of the question. The second question about the numbers. We know that in developed countries we have 28 cochlear implantations per year per 1 million inhabitants. So that's roughly 2,500 in Germany, and it spreads all over. We see that the numbers are drastically low in the second world. In China, it's a fraction really of those 28. It's below 1 per million. Okay, and what we see in the end, I didn't talk about this today, but the believers of the community that when we have a machine going through the mastoid, and we effectively will also use the machine to go into the cochlea, we can avoid the trauma in the cochlea, because effectively when you drill a hole in the cochlear wall, you destroy any residual hearing in the cochlea. Okay, but with the robot, you can actually be so sensitive that you stop at the membrane. You can cut the membrane open with a small knife, and you can go in. So all of our hope is to, at the end, be able to place electrodes in an atraumatic way into the cochlea, and this would open up the indications for cochlear implants, because right now you implant them only in patients where there's no residual hearing, because you kill all the other hearing afterwards. But if you're able to put implant electrodes into the cochlea that stay and that go in, and you preserve the residual hearing, then this is a big boost. So we are not there yet. This is a step that comes into the future. This is really where we have the hope, because we can do process control.
Take one last question.
Thank you for your talk. My question is related to imaging. Do you do any further validation of the imaging during the drilling, and are you able to correct? And a sub-question on that, for reaching that level of resolution in CT, can you comment about the dose that you use for that?
Right. Thank you for the interesting question. So imaging usually is the problem of effective resolution that is important for the accuracy. It's about the diagnostic radiological quality. You have to see things, right? If you have a high resolution but you don't see things anymore, it's useless. And the third part is dose. Okay, so cone-beam imaging is actually very favorable compared to computer tomography systems. The level of effective dose is on the order of 3 to 5 to 6 times lower than that of computer tomography. So that plays for us, although we see that the accuracy, the radiological quality is less good in the computer tomography, but it increases all the time. So there's really a lot of movement in this whole systems going on. At the moment, we are comfortable. We are more concerned with the patient movement in the imaging during the imaging acquisition. That's something we need to deal with. And also the question of what happens with the slight distortions. As you can imagine, if you have a system, if you scan the patient, you get a stack of pictures that in the computer go together very nicely, perpendicular to each other and so on, but in reality, it's a mechanical system that records the images and it creates distortion and so on. So we need to cope with this. This is the challenge.
Thank you.
Will I talk afterwards? Yeah,
I'm sorry, we will have another chance. We have a round table session at 3:30 in the method of robotics trial. So let's thanks Stefan again.